My third problem will be a little bit typical, not because of the function, but because of the region. So one of the things which I've observed over a period of time is the sort of cautiousness among students in figuring out the region of integration. Because you'll have to be good at two things in this advanced calculus. One thing is you must know the region geometry. According to the region geometry, you must pick up a proper coordinate system in which the evaluation can be performed. So students get a bit jittery whenever they see problems like this. But all that needs is a little bit of exposure and some constant practice. So in this question again, the function is not what we are worried about, but it is the region description. I can sense from these last two equations that there is a circle here, there is another circle here. Of course, you must be very careful with this one because the center is not at the origin. That has got center at the origin, but not this one. So we'll have to really work on this and see what exactly it is and how this is connected to that. Then of course this is simple language. X greater than 0 means the portion to the right of the y-axis, and y greater than 0 means the portion above the x-axis. So which means essentially whatever we are going to draw will be in the first quadrant. So this part is understood. Some region in the first quadrant. Let's begin from there. This is a circle with center at origin with radius 2. But this is not straightforward. You must do a little bit of manipulation. So we can write x squared minus 2x, add 1 to complete the squares, but balance it out by using a 1 on the right hand side also. Whatever you create, you must nullify. So this would make it x minus 1 whole square plus y square is equal to 1. Now things are becoming clear. The center of this circle will be 1, 0, which means it has center on the x-axis and the radius is 1. So let me first draw both the circles, then take this information into account, then shade the region. I will first draw a circle of radius 2 with center at the origin. We have this part. I will just show the coordinates for easy plotting. This will be minus 2, 0. And this will be 0, minus 2. So just draw this circle. Now we come to this circle. First locate the center 1, 0. It happens to be the midpoint of these two. So it will be somewhere here. And the radius is 1, which means this is 1 unit. This is 1 unit. Therefore, whatever is the circle we draw will have this point as the center and having these 2 points as the extremities of a diameter. So that circle is relatively a smaller one. Its radius is exactly 50% of the bigger circle. Now there is a very careful requirement to understand which region to shade. The language is very clear. That portion to the right of the y-axis, above the x-axis, and between these two circles. So, shade that portion. Shade that portion. So, this region looks completely different from the last two regions that we just handled. In any case, the region is bounded by circles. Circles are the simplest of the polar curves. So I have decided, or that will be the natural choice, to convert the problem into a polar double tick. Back to the basics, use x is equal to r cos theta, y is equal to r sin theta, x square plus y square will make it r square. Once again, that's a very big gain because this is going to become the square root of r square. And then, of course, dA would be r dr d theta. Now comes the most important part, the limits for theta and r. So, let us first observe the figure carefully and fix theta limits. You can see that this region grows from the x-axis. Of course, it widens its area, but ends up with the y-axis exactly. So it begins with the x-axis, grows, and stops at the y-axis. So there is no problem with the theta limits. Now comes a very important aspect of this problem, fixing the r limits. This circle equation, I mean the circle with center at the origin and radius 2 units, coming from this equation, has to be given some r. Similarly, this circle coming from this equation, or rather this equation, should be given some r. So let us take x square plus y square is equal to 4. This gives r square is equal to 4. We take r is equal to 2. We take this circle whose equation is this: x squared plus y squared minus 2x is equal to 0. R square minus 2 times x is to be replaced with r cos theta. So I have two solutions. R is 0 or R is 2 cos theta. We can see that I now have 3 R's and I'm still not done with it because there is also one more boundary, x is equal to 0. So you must derive your R limits from all the boundaries which participate in the region formation. So I've used this, I will now have to use x is equal to 0. So x is equal to 0 would give me R cos theta is equal to 0. This offers two solutions, r is equal to 0 or theta is equal to pi by 8, because cos theta vanishes when theta is pi by 8. Now look at the spectrum of values that we got for theta. We have to choose two which represent all. So what I will do is, I will choose this right here, r is equal to 2, this is r is 2 cos theta. The r limits can be taken as 2 cos theta to 2. But how do you decide? Why did we draw r is equal to 2? Because r is equal to 2 is explained by 2 cos theta. In fact, I have taken r is equal to 2, let us say, not concerned about it. But why did we drop r is equal to 0? I dropped r is equal to 0 because we have in the theta range pi by 2. And When I use pi by 2 here, I'll get 2 times cos pi by 2. Cos pi by 2 is 0. So I get r is equal to 0 from 2 cos theta. That means it takes into account the r is equal to 0. So I don't have to worry about this because r is equal to 0 is explained by 2 cos theta. Then you may say, why did you not drop r is equal to 2? Because I can get r is equal to 2 from 2 cos theta for theta is equal to 0. Now here is where you have to understand carefully. You see what are the physical boundaries. This is a physical boundary and therefore that r can be directly used. So this is a physical boundary, this is a physical boundary, that is a physical boundary. So r is equal to 2 I take straight away. And r is equal to 2 cos theta I will take because this will also have r is equal to 0 explained for theta is equal to pi by 2. So this is the very, very important part of this problem. Now the evaluation part is the easiest. Theta varying from 0 to pi by 2. R varying from 2 cos theta to 2. dA will be replaced with r dr d theta by the square root of r square. So these two can be cancelled. I'll have 0 to pi by 2, integration of 0 to 2, dr d theta, not 0 to 2, but 2 cos theta to 2. So that would make things extremely easy. The integration of dr will be r from 2 cos theta to 2 d theta. So 0 to pi by 2, 2 minus 2 cos theta d theta. The integration of 2 with respect to theta is 2 theta. The integration of 2 cos theta will be 2 sin theta. So that will make it 2 times pi by 2 minus 2 times sin pi by 2 with the lower limit not contributing anything. So your output will be pi minus 2. So there is something to learn from this example. One thing is how to understand drawing the region itself and how to fix your r limits in particular. There is no confusion about the theta limits. More and more of such problems will be very, very useful in the long run. So let us wind up this discussion with one final problem where instead of using circles every time, I will take you to a new polar curve. This is a problem I've selected because I wanted to expose you to a new polar curve. Here, 2 cardioids are involved. As you can sense, there is something to do with cardium, the human heart. This particular shape resembles a little bit like that, a cross section of the human heart. So, let us imagine the polar reference frame. Theta is equal to 0, theta is equal to pi by 2. Then this theta is pi, and this is theta is 3 pi by 2, or that is minus pi. Now, how does r is equal to 4 times 1 plus cos theta look like? This is how it looks like. This in the polar system is called the pole. The pole is the origin of coordinates in the polar reference frame, just very similar to the origin in XY coordinate system. So the equation of this cardioid is r is equal to 4 into 1 plus cos theta. the reflection of the same cardioid in the line theta is equal to pi by 2, which can be compared to the y-axis, is the other cardioid. So I will draw the other cardioid. Make it a little bit more symmetric. So these are mirror images of each other. So the problem is to find the this integral, which is common to both this cardioid. So it has to be this part, common to both. So in order to do this, the straightforward approach is take this part, I will give it a new shade so that it's identifiable. So I will just integrate over this part and just multiply 4 times because the remaining 4 segments are also covered. So I will call this shaded portion R prime, which means the problem double integral dA over R is the same as 4 times double integral dA by R prime. So it is enough to describe the region R prime in the polar coordinate system, and you can see that this cardioid varies from the x-axis, so-called x-axis, to the y-axis. So theta varies from 0 to pi by 2. And let us look at the variation of R. R is equal to 0 to. Because we have chosen to work on this part of the region, I will take this boundary. This boundary is not that. It belongs to the R is equal to 4 times 1 minus cos theta. So just once again to explain, this boundary is part of this cardioid. R is equal to 4 into 1 minus cos theta. So that will be my outer limit. The rest is all very simple. Fix your limits 0 to pi by 2, 0 to 4 times 1 minus cos theta. This dA will be replaced with R dr d theta. And the rest is all straightforward. So 4 times 0 to pi by 2. The integration of this part would be R square by 2. 0 to 4 times 1 minus cos theta d theta. So this would cancel 2 times. Replace R with 4 into 1 minus cos theta. I'll get 16 times 1 minus cos theta whole square minus 0, which I need not write. So this integration should not be messed up with. There are 2 options. You straight away go for an expansion, or use to convert 1 minus cos theta as 2 sin square theta by 2, which is unnecessarily going to complicate. So I'll just expand it. 1 minus 2 cos theta plus cos square theta d theta. All integrations are straightforward. The integration of 1 with respect to theta is theta. The integration of 2 cos theta is 2 sin theta. So I will separate this out, 0 to pi by 2. And I will handle 0 to pi by 2 cos square theta d theta integration exclusively, because this does not blend with this. So 32 times pi by 2 minus 2 times sine pi by 2, that is 2 times 1, lower limit doing nothing, and we have seen several times the integration of 0 to pi by 2 cos square theta will be pi by 4 straight away. That can be remembered forever. So this would be 32 times pi by 2 plus pi by 4 would make it 3 pi by 4 minus 2. So let's do some simplification. You can take the LCM, which is 4, that cancels 8 times. We'll get 3 pi minus 8. So we have studied a problem that did not really challenge the integration, but the region understanding became very, very important. In fact, you will know very soon that what we did is a very, very important concept. The double integration of dA always produces areas. So we in fact just estimated the area of this shaded region. But doing it in polar would be the most sensible thing to do. We can't imagine doing it in other coordinate systems.